Imagine this. A star, many times bigger than our sun, reaches the end of its life. It explodes, and then, instead of disappearing, it collapses into something so dense, so powerful, that not even light can escape. That is a black hole. Black holes are not science fiction. They are not cosmic vacuum cleaners sucking everything in. They are real objects in our universe, time, and even reality itself. Today, we are going to explore everything you need to know about black holes, from how they form to what happens if you fall into one, and why they might hold the deepest secrets of the universe. So take a deep breath and let's begin. A black hole is a region in space where gravity is so strong that nothing can escape. Not matter, not light, not information. Literally nothing. They are one of the strangest, bizarre objects that exist in the universe. They are very dense. Imagine squeezing the mass of the sun into a space smaller than a city. That's how dense it is. Imagine a full mass of sun is just packed in a city size. How much powerful gravity it will have. At the center of a black hole lies something called a singularity, a point where density becomes infinite and the laws of physics break down. We don't have exact idea what singularity exactly is. Our current physics breaks down and cannot define what happens in the singularity. Surrounding it is the most famous boundary in space, the event horizon. Once something crosses the event horizon, there is no coming back. The space and time is wrapped in such a way, every possible directions only lead to the singularity. The event horizon is a point of no return. It is not a physical surface. It is not a wall, neither it is some kind of physical barrier. It's a boundary in space-time. After crossing the event horizon, every possible future leads only deeper into the black hole. There is no direction. Only possible path is now singularity. It is true even for fastest thing like light. If you're watching from the outside, an object falling into a black hole never really seems to cross the event horizon. As it gets closer, it looks like it's slowing down, fading, and just frozen in time. For the object, it falls steadily toward the black hole. From its own perspective, it crosses the event horizon without noticing anything unusual. Time feels normal, and nothing appears frozen or slowed. It just continues its fall inward. Most black holes form from massive stars. In space, huge clouds of gas and dust collapse under gravity. When enough material finally gathers together, a massive star is born. For most of its life, the star remains stable. Deep inside its core, something takes place, a nuclear fusion. Hydrogen atoms fuse into helium, releasing a massive amount of energy. This energy pushes outward, balancing the constant inward pull of gravity. As long as this balance exists, the star continues to shine. This phase continues over millions of years. Then, the star begins to run out of fuel. Hydrogen in the core is exhausted, and the star starts fusing heavier elements, helium into carbon, carbon into oxygen, and eventually into iron. This process happens faster and faster. Iron marks a turning point. Unlike other elements, iron fusion does not release energy. When the core becomes mostly iron, the outward pressure suddenly drops. The balance is now gone and gravity wins. With no force left to resist gravity, the core collapses rapidly in just a few seconds. The collapse is so intense that protons and electrons are crushed together, forming neutrons. The core becomes incredibly dense. This collapse triggers a massive explosion called a supernova. The outer layers of the star are blasted into space, spreading heavy elements across the universe. The remaining core decides whether the star will become neutron star or it will collapse to black hole. If the core's mass is less than about 3 times the mass of the Sun, the core stabilizes as a neutron star. However, if the core's mass is greater than about 3 solar masses, gravity becomes too strong. There's no known force left to stop the collapse. The core continues shrinking, becoming smaller and denser. Eventually, its escape velocity exceeds the speed of light. At that moment, an event horizon forms. Once the event horizon appears, the object becomes a black hole. Stellar death is the most common path for black hole formation, but this is not the only way black hole forms. Collision of 2 neutron stars can also create a black hole if mass is enough to make it collapse in its own gravity. Supermassive black holes are created by the direct collapse of massive gas clouds without any star phase. Falling in a black hole is not a pleasant journey. It is not peaceful. It is not calm. It is one of the most terrifying experiences the universe can offer. So what happens? Short answer is you die. Okay, this answer is not satisfactory. The death process is far more terrifying. The gravity acts too strong at your feet compared to head. You die in the process called spaghettification. And yes, this term is real. You will be stretched and pulled into a long, thin shape, like a spaghetti. In stellar mass black holes, spaghettification would happen even before crossing the event horizon. In supermassive black holes, you could cross the event horizon first and only experience spaghettification much later. Einstein showed us that gravity isn't just a force pulling things down. It bends space and time together. Space and time are not separate things, they are woven together into a single fabric called space-time. When something massive exists, like a star or a planet, it presses down on this fabric, creating a curve. A black hole is the most extreme version of this. Its mass is packed into an incredibly small space, so the curve becomes unimaginably deep. Space doesn't just bend here, it plunges inward. And when space bends this much, time is forced to bend with it. This bending of time is what we call gravitational time dilation. It means time actually runs slower in stronger gravity. Imagine 2 identical clocks, one far away in space ticking normally and another close to the black hole. From the distant clock's perspective, the one near the black hole ticks much slower. A second there might last minutes or even years here. So why does this happen? Think back to our space-time fabric. When a massive object like a black hole warps it so deeply, paths through time get stretched out for anything in that deep gravitational well. Light or signals trying to climb out of that curve have to fight harder against gravity, taking longer to reach us. So to a faraway observer, everything near the black hole appears to slow down. If object is close enough, time dilation becomes infinite. From outside, anything approaching the horizon seems to freeze forever, fading away but never quite crossing. Yet, for the person falling in, time feels normal. They fall in normal time. This extreme slowing of time is why black holes are like cosmic time machines. Spend a short while orbiting close to one, and when you return, the universe could have aged thousands or millions of years. Although black holes are cosmic monsters, they are not actually immortal. For a long time, scientists believed black holes were immortal. But in the 1970s, one scientist changed everything. Physicist Stephen Hawking discovered that black holes aren't completely black. They actually glow, very, very faintly. This glow is now called Hawking radiation, and it means black holes can slowly lose mass and eventually evaporate completely. Yes, black holes can die. Empty space isn't truly empty. Because of quantum uncertainty, tiny particle-antiparticle pairs are constantly appearing and vanishing everywhere in the universe, even at the edge of a black hole. Most of the time, these pairs destroy each other instantly, but right at the event horizon, something extraordinary can happen. One particle falls inward, lost forever. The other escapes into space. That escaping particle becomes real, carrying energy with it. And to keep the universe in balance, the black hole itself loses a tiny fraction of its mass. But this process takes a lot of time. A black hole with the mass of our sun would take about 10 to the power of 67 years to completely evaporate. That's a 1 followed by 67 zeros. Far longer than the current age of the universe, which is only 13.8 billion years old. Supermassive black holes at galaxy centers will take 10 to the power of 100 years or more to evaporate completely. Black holes remind us of something important. The universe isn't gentle, it isn't simple, and it doesn't owe us understanding. Yet, here we are, small beings on a tiny planet, thinking about the darkest objects in the universe. And somehow, that's beautiful. If you enjoyed this journey into the universe, go ahead and like the video, subscribe, and share your thoughts in the comments. Until next time, keep exploring.